lab at Johns Hopkins. Today I will be presenting our work on end-user interface for robot programming. Robot programming have the potential to enable general-purpose robots to augment human ability in many domains. It could enable robots to work collaboratively with our human workers. It could help us meet the demands both physically and psychologically of our aging population. It could also help small business owners to set up more flexible and agile manufacturing lines in the future. In order to enable robots to help us in these applications, end users will need to be able to reprogram their robots for their custom tasks. But what is keeping us from end-user robot programming? Well, unlike industrial robots in factories, fenced and caged, keeping away from the user, personal robots faces more complicated tasks, more unpredictable environments, and possible human involvement. It needs to work along with the human. And these factors make robot programming a complicated problem. Now, let me tell you how robot programming is done today. The most obvious and possibly the most flexible way of programming a robot to do a certain task is by writing code. Programming robots to perform custom tasks usually needs experienced engineers with knowledge in robot programming frameworks, as well as background knowledge in robot perception and manipulation. As an example, a group of professional robotic engineers from Willow Garage once tried to program a PR2 robot to fetch beers from a fridge, and it took the group 5 days to implement it. Robot programming is time-consuming, even for professionals, so just imagine how it would be for users without technical training. The prior research has explored methods for easier end-user robot programming. A common method is programming by demonstration. Programming by demonstration aims to transfer human skills to robots. Specifically, a human will teach a robot by physically showing the robot how to perform tasks, as what the woman is doing in the picture. The strength of such method is that it simplifies the motion planning of robots, because a human is essentially do the planning for them. And it will also enable more complicated and human-like maneuvers. But it is not without weaknesses. First of all, it's hard for robots to deal with the dynamic environment with the pre-programmed learned task. And you usually need multiple demonstrations of the same task to deal with different configurations. Another method commonly used in end-user robot programming is visual programming interfaces. Perhaps the most successful and most well-known visual programming interface is the LEGO Mindstorm Robotics kit. It uses a flowchart-like graphical interface, and it's aimed at children, so its functionalities are simple by design. This kind of interfaces abstracts low-level programming and allow users to focus on high-level task planning. But the extra-level abstraction alienates the user from the real world, making it hard to specify real-world objects and locations in the graphical interface. And that's why it is usually combined with other methods like programming by demonstration. Now, let me give you an example of the current state of our approach in end-user robot programming. The UR5 robot is a collaborative robot that is commonly used in flexible manufacturing. It employs a combination of programming by demonstration and the visual interfaces as its built-in programming method. At the motion level, the user would manually move the robot or move it with the virtual joysticks and record the waypoints for later use. At the task level, the user could rearrange the recorded actions in the graphical interface with conditions, loops, and interruptions for complex task planning. While this combined method of programming by demonstration and visual programming works well, it has a major limitation where the object referencing is indirect, meaning that it is not easy to specify objects of interest using this method. In this work, we aim to address this limitation of indirect object referencing. We developed PATI, a proof of concept system that allows users to reference objects directly in a situated manner. The PATI system consists of a robot, a top-down projector, and a 3D camera. In designing PATI, we drew inspirations from traditional GUI design and the touch-based interaction. We treat real objects as a part of the user interface with which you could interact. We augment the workspace with a projected interface where the user could use common gestures to specify custom tasks. With integrated vision-based detection and tracking, the projected GUI in workspace allows users to reference objects in situ while specifying robot tasks. Well, the pick-and-place task is one of the most common and fundamental tasks in flexible manufacturing. Now let me give a step-by-step example of programming a pick-and-place task in PATI. First, the user would instantiate a tool to select objects on the side menu, where a list of tools for different purposes are available. The tool is shown here as a blue circle, and the user could resize it and move it so that it encloses the objects of interest. Then, the user would do the same thing for a tool that selects an area as the destination of the pick-and-place task. This tool is displayed here as a magenta square. Then, the user would specify the task to be performed by putting an arrow pointing from the objects to the destination. The properties of the arrow, which includes the task, the objects of interest, and the destination, could be specified in a circular pop-up menu. After the user specification, the robot performed the task as it pick and place all the objects selected. Now, let me present our user evaluation of the PATI system. Our goal here is to compare the PATI system with the current state-of-the-art, the UR5 built-in method. We designed the within participant study with two conditions, the PATI system and the UR5 built-in method. The conditions were counterbalanced in the experiments. We employed 5 measures to assess the task performance and the usability. In particular, we measured task time, number of task mistakes, number of task questions, practice time, and the task loads. The experiment's procedure goes as this. For each condition, the participants was given materials to teach them how to use the interface. Then the participant would practice on the practice task. When the participants feel comfortable to move on, the experimenters would ask them to use the interface to program a designed experimental task. After finishing the task, the participant was asked to fill out a questionnaire regarding their experience with the interface. In this study, we recruited 17 participants on the college campus. Today, I'm going to highlight 2 results from our study. For the complete results, please refer to our paper. First, let me show you the task time. We measured the time taken for the participants to finish the experimental task. We found out that the PATI system allows participants to complete their task 66% faster than the UR5's built-in method. Regarding usability, we measured task loads using NASA Task Load Index. We found that the users reported less task load using PATI system compared to the UR5's built-in method. To summarize, our results highlighted that the PATI system could improve the task performance and user experience in robot programming. And as a conclusion, we believe that a lot more needs to be done to enable accessible end-user robot programming. And today I present you PATI, a prototype system that moves toward this goal. The current project has some limitations that could motivate further research. As a next step, we want to explore the expressivity of the system and to expand its capabilities beyond pick-and-place related tasks. And our project is open source through our lab's GitHub. Thank you all for listening. And with that, I would be happy to take some questions.
Thanks for the presentation. So for your workload measurement, I was wondering, are there any reasons that you only adopt 3 constructs to measure the user's workload? You know, for Lanza TLX, they have 6 or 7 constructs, but you only adopt 3 of them. Can you explain that?
Because of the property of the task, some of the measures in the NASA task load index are not like relevant to our task. That's why we rule them out in the questionnaires.
I was thinking this kind of techniques can work in static scenarios. I mean, if the robot moves, then it becomes difficult to use a projector.
Well, yes, we think about that. Actually, that's one of our future directions. We want to integrate the projection and the detection hardwares with the robot, so that as the robot moves, the GUI and the workspace moves with the robot.